Okay, then, am I audible?
Yes, sir.
Okay, thank you. So, I guess we can start. And so, okay, then welcome to the week 3 of the problem solving session for the Introduction to Fluid Mechanics course. So, just a second. Okay, so just as we can see on the screen here. So this week's content is relatively, comparatively smaller. So I think the class will not be that long, but still, following the general agenda that we follow for all the sessions, I will briefly discuss the topics that was covered in this week's session, and then obviously I will hope it to be an interactive one. So if you have any doubt regarding any concepts, you can very like openly ask the doubts, and then after discussing the concepts briefly we'll go on to solve some questions regarding the discussed topics that will help you to solve the problem that is asked in your this week's assignment. Okay, so this is the agenda for today's session. So with that, let us begin today's session. Okay, so these are the three topics that was discussed by Professor Chakraborty in the lectures. It is surface tension, fluid statics and its corresponding governing equations, and the basic principle of manometry. Okay, so these were the three topics that were discussed by Professor Chakraborty. And since there are three students in the class, I would like to know from like any one of you, like what do you understand by surface tension? Like, please be free to answer it. Like, there's always something written on the screen, but you can go ahead and find different different explanation for the same. There's no issue. Please go ahead. What is surface tension, or where are the instances that you feel that you come across surface tension in your day-to-day life? So can you please give an example or try to define the same? Arun, if you're in the class, can you please go ahead and explain like what do you understand by surface tension? Arun? Well then, Gokul, are you in the class? Okay, then Sonalika, can you go ahead?
Yes, sir.
Yes.
Yes, sir. So it is the stretching membrane. That is, it is due to the cohesive force surface tension is occurring.
Yes, yes, yes. Very good, very good. Yeah, it's a very good, nice definition. So, where are the instances that you feel that you have observed surface tension in your day-to-day life? Like, can you give an example?
Yes, sir. So the water droplets.
Oh, yes, yes, yes. The video shown by Professor Chakraborty, right? In the
Yes, sir.
lectures. Yes, yes, excellent. So, thank you, Sonalika, for interacting. And Gokul, I insist you also to have an interactive session so that it's beneficial for both you and me as well, right? Okay, then. Right. So, thanks, Sonalika. And as she rightly pointed out, that surface tension is basically the property of the fluid to maintain its structure, and while doing so try to have a smallest surface area. Okay, and this uh, this property of the fluid to maintain its structure comes along with a inherent force that arises because of the cohesive forces that exist between the water molecules. Okay, so This is the example. This is an example that was discussed by Professor Chakraborty. Like, for example, if there is water molecules above the liquid surface, right? Say this is one of the water molecules, and this molecule is interacting both with the atmosphere, that is air, and the liquid below it, right? And this molecule will contain various other number of molecules that will have certain cohesive forces between them, okay? And since the cohesive forces between the water molecules and this particular molecule is greater than the forces between the air molecules and this water molecule, there will be a net resultant force towards the downward direction. But still we see that these molecules maintain its integrity, and this maintenance of the integrity of this water molecule is by the virtue of the surface energy, and this force that exists to maintain this its integrity is known as the surface tension, okay? So by general I mean just look, okay, by the general way in which we address surface tension is through the help of a surface tension coefficient, okay? And its units are force per unit length, where this force is the surface tension force and L is the perimeter of the molecule or the any surface that is interacting on which the surface tension force is interacting, okay? So I guess this part was this diagram was discussed by Professor Chakraborty, and he derived the excess pressure that exists within the bubble or the droplet to maintain its integrity, okay? So it was given by delta P is equal to sigma 1 by R1 plus 1 by R2, okay? I will not go ahead and derive the complete derivation, so I will just ask you to, if at all you have any doubt, go back to the lectures and then revisit it, okay? So Sonalika, is it clear up till this point?
Yes, sir.
Okay, so kindly bear with me, okay? Just we will go just briefly go to the concepts and then we'll discuss the problems, okay? That will help you to solve your assignments. Is it okay?
Yes, sir.
Okay, thank you. So then there were some special cases as discussed by Professor Chakraborty regarding the expression for excess pressure in the case of a spherical droplet and spherical bubble, okay? So can you please tell me, like, what's the main difference between a spherical droplet and a spherical bubble? Or before that, like, why we are considering the excess pressure instead of the absolute pressure in the case of this surface tension? Like, why we are discussing the excess pressure instead of the absolute pressure? Can you please tell? Okay, that's fine. See, the excess pressure comes from the perspective that since this liquid bubble is able to maintain its shape, its integrity, there is obviously an atmospheric pressure outside the bubble, and similarly there is an inherent pressure within the bubble. But in order to maintain its shape, there must be an excess force that is being exerted outwards to maintain its spherical shape, okay? And this pressure is always greater than the surrounding atmospheric pressure, and that's why it is the excess pressure that is of interest rather than the absolute pressure in the case of analyzing the surface tension effects for that is required to maintain the integrity of the spherical droplet and the spherical bubble, okay? I hope it was clear.
Sir, please again.
Which part?
Sir, such in what pressure the Rajagolya Samukra?
Excess pressure.
Yes, sir, yes.
See, yeah, that only. See, this spherical bubble is able to see when you see a water droplet or a say soap bubble, okay, in say while you're washing clothes or taking bath, you see some soap bubble, right? Soap bubble that comes out while you're splashing the soap solution, or say if there is rainfall, the water droplet that falls down is able to maintain its shape, right? It's able to maintain its shape, that
Yes,
spherical
sir.
shape. Yeah. First of all, it is of spherical shape. Why? Because for a particular given volume, the sphere would have the least surface area. Okay, that's the first thing, and that happens because of the cohesive forces that are there inherent to the water molecule that are able to uh, maintain its integrity because of the forces, the cohesive forces that are exerted on its surface, right? As you rightly mentioned in the start of this today's session, right? Okay, is it clear?
Yes, sir.
Yes,
Yes, sir.
yes. But see, if if at all a case, if at all a scenario arises that the pressure within the bubble is lower than the surrounding pressure, what would have happened? The bubble would have taken a, what to say, a distorted shape like this, right? Something like that. It would have,
Yes, sir.
yes, it would have deflated, right? But rather, it is able to maintain its shape. Apart from it, it is also an additional force that is trying to collapse collapse it collapse it even further, right? To have the least possible surface area, right? So there are two forces. First is the outer atmospheric pressure, and also the forces that is trying to compress it even further, right? So there are two forces that the inner pressure has to overcome to maintain its shape, right? And that's why the inner pressure is always larger than the outer atmospheric pressure. Okay, and this expression that was
Yes.
derived, yes, that was derived is for the this excess pressure. This del P plus the P atmosphere would give you the absolute pressure that is within this liquid bubble or the spherical bubble, liquid droplet or the spherical bubble. Okay, so that is the concept excess pressure. Why there is an excess pressure within these bubbles? Because it has to overcome the atmospheric pressure as well as the surface tension effects. Is it clear?
Yes, sir.
Okay. So these are the expression that was derived by Professor Chakraborty. So I will not go ahead and derive it again for the sake of saving time. Okay. And again, there is an expression for liquid jet as well, if I'm not wrong. So that is basically for liquid jet, delta P is equal to sigma by R. Okay, that's the expression. Okay, then. So now we'll go to uh, the third topic that was discussed in the lecture, that is the concept of capillary rise. Okay, it's also one of the implications of surface tension, uh, and can like, okay, I guess it's obvious through the image here, but have you like ever observed capillary rise in your, say, in your lab experiments or in your day-to-day life, or any phenomenon where capillary rise is very important in our day-to-day life? Can you give an example? Sonalika?
Yes, sir.
Yes. So can you give an example where capillary rise you've observed or it's important in our day-to-day life?
Sir, when a thin tube is
Mm-hmm.
put inside a large tank or a beaker, then there is a rise in
The water.
water level.
Yes, yes, exactly, exactly. So actually, like, if you would have observed in your, say, in your chemistry labs, there are very thin capillary tubes there. And if you put that thin capillary tube in the, say, in a liquid, in a water glass or any liquid container, you'll see there is a rise in the water level within the container. Just wait for a minute, okay? Just a minute. Okay, I apologize for the delay. Yes. I'm audible, right?
Yes, sir.
Yes, sir. Yes, I'm sorry for the disturbance. Okay. So these are the instances when you see capillary rise, right? When you just insert a thin capillary tube, by the name itself, it's known as capillary tube, in a water container, you'll see there is a capillary rise. And that rise is primarily because of the adhesive forces between the water and the glass, between the water molecules and the glass surface, right? And also, one of the very important natural phenomenon where capillary rise takes place is in the case of the roots of the trees, okay, or specifically the vascular bundle of the trees. There also, even though the primary, see, in the tall trees, the water has to go up through the roots, right? Through the roots or the vascular bundle, the xylem and the phloem in the case of trees, right? So, this rise in the water level, even though it is primarily because of transpiration, but still a certain rise in the level of water through the roots is by the help of capillary rise. Okay. Uh, I guess, yes, I guess Professor Chakraborty might have given this example. I'm not sure because I'm not able to recall, but this is one of the very important applications of capillary rise in the case in our day-to-day life. Okay, and obviously there can be n number of research on it, but in a very vast scale in our day-to-day life, this is the one of the very fundamental applications of capillary rise. Okay, because the roots of the trees, like you may say that they are very thick, and it's very difficult to imagine capillary rise because you know that the capillary rise occurs for for very thin tubes, right? But the vascular bundles or the vascular tissues of the trees are, if you look closely, are very, like, very small shaped tubes within the roots, something like that seep the water from the soil and what to say, take it up to the stem of the tree. Okay. Okay then. So I guess that's all. And again, capillary rise depends on these 5 factors. So I guess I don't need to go again. Professor Chakraborty would have definitely discussed about it, so I don't think I need to go through that. And this is the fundamental, what to say, formula for the capillary height in the case of uh, liquids, in the case of liquids and hydrophilic surfaces. Okay, or specifically in the case where the uh, the angle theta or the contact angle is an acute angle. Okay, so can you tell in the case of which liquid, like if you have attended the lectures, the contact angle is greater than 90 degree? Can you tell an example of a liquid?
Mercury.
Yes, absolutely. So see, look at this diagram now. So this is a diagram for the capillary rise in the case of water, okay, or in the case of any fluid that forms an contact angle which is lesser than 90 degree. Okay. So what happens is this case that the adhesive, there are two types of forces that are currently acting on this liquid column. So or in the molecules that are within this liquid column, okay, specifically the molecules that are within this liquid column. First are the cohesive forces between the water molecules that act among each other, and second is the adhesive forces between the water molecules and the glass surface. Okay, so in the case of water, what happens is that this adhesive force is comparatively larger than the cohesive forces between these water molecules, and that's why you can see there's the structure itself shows that the water is being, these attractive forces are pulling the water out of the uh, bottom surface of the tube. Okay, but since as you mentioned, in the case of mercury, it will form an angle, say some contact of it, say something like this, that is larger than 90 degree. So what do you think happens uh, to the adhesive and the cohesive forces? So what is this relation in the case of mercury?
Positive. cohesive force.
What? What?
Sir, adhesive forces is less than cohesive forces
Yeah.
in case of mercury.
Yes, absolutely right. So in the case of mercury, as you rightly mentioned, the adhesive forces within the mercury molecules is comparatively larger than the sorry, comparatively lesser than the cohesive forces between the mercury molecules. I will just redefine it. What that is basically what happens is that the adhesive forces between the mercury molecules and the glass surface is lesser than the cohesive forces between the mercury molecules. Okay, and that's why you can see that instead of it being pulled by the glass surface, the cohesive forces between the mercury molecules is actually pulling back the uh, uh, the level of mercury within the capillary tube. Okay, and you can see the contact angle that's formed by the tangent to the surface of the meniscus is actually an obtuse angle. Okay, it is greater than 90 degree. So in such
Yes.
kind of okay, yes, so in such kind of fluids, the formula for the capillary rise is given by this equation. Okay, so obviously if you want to get to the detailed derivation, I will just suggest you to go and revisit the lectures, and it's basically just the force balance, the balance between the weight of the liquid within this column and the surface tension force that exists between the mercury molecules and the glass surface. Okay, that's all, but it is highly suggested that you just go back to the lectures and just revisit the derivation so that it's very fluent for you to go through such problems. Okay, so finally we have come to the final topic for today's discussion, that is the principle of manometry. Okay, and manometer is specifically used to measure the pressure difference between any 2 points in the case of any, say, a pipe system or any piping system, or even you can use the principle of manometry in the case of measuring, say, static pressures in the case of a liquid container, or any say in the case of ventimeter as well. So these are the places where the manometer is useful and the principle of manometry comes into picture. Okay, so are you clear regarding the concept of manometry, like how the derivations are done to measure the pressure difference between these 2 points?
No, sir.
Okay, thank you. Thank you. It's very good to be clear. So, I'm sorry. So actually, I would say that this is one of the very simplest derivations if you know the concept. Okay, that's the catch. Okay, so let us dive a bit deep in this concept, because if you are clear with this concept, I don't think you will face any problem regarding manometer, and any kind of problems, like any kind of problems regarding manometer you will be able to solve. Okay, if you are able to catch the concept now. Okay, so assume that it's a pipeline here, and the flow is occurring from A to B. So let me just okay. So in this case, can you tell me at which point the pressure do you think that it should be higher? Point A or point B? Just a wild guess. Just a wild guess. It's fine.
So point A.
So you suggest that pressure at point A should be greater than pressure at point B. Okay.
Yes, sir.
Okay. So was it a guess, or just you have some conceptual reasoning behind that?
No, second.
Yes. Okay. So fortunately that's correct. The pressure at point A is greater than pressure at point B. Okay. See, this is something that you need to remember throughout the course, and you will see how we are able to mathematically derive this the reasoning that you have put right now, that pressure at point A should be greater than pressure at point B for the flow to occur in this direction. So if you are remaining throughout the course of this introduction to fluid mechanics course, you will eventually see that this concept of having a negative pressure gradient Negative, why? Because the pressure at point B is lesser than lesser than the pressure at point A, and that's why the pressure gradient would be something negative, right? Because as the distance is increasing, the pressure is decreasing, so the gradient is negative. And you will see that this is one of the very fundamental factors that drives the flow in pipes. Okay, this negative pressure gradient is one of the fundamental driving forces in the case of flow through pipes. Okay, so that's just a thing to remember, this negative pressure gradient, so that you are able to correlate when we discuss thoroughly flow through pipes. Okay, then thank you. So as you mentioned, the pressure at point A is greater than point B. Okay, so in the case of manometers, say this is the diagram. I hope the diagram is clear. Yes.
Yes, sir.
Okay, so you can clearly see that the liquid level, say the heavier liquid, in this case let us assume that this blue liquid is mercury. Let me just label it. The blue liquid is mercury, and the transparent liquid that is flowing through the pipe is water. Say it is water. Okay, don't go to the color scheme, it's just something that I use for my convenience, but it's fine. Okay, so this blue liquid, that is mercury in this case, the liquid levels are shown here in this U-tube manometer. Okay, U-tube shaped manometer. So liquid level at point C is mentioned here in this point, and the liquid level at the other arm is at here. Okay, say this point, say let us label it as E. No issues, we can label it as E. Okay, so just now let us just label these heights. Okay, these heights and the height difference are very important or very crucial in the case of measuring pressure differences through the help of manometer. Okay, and Sonalika, since you are the only student here now, right now at present, you can just stop me anywhere you want. Okay, if you want to have any doubt, just stop me at that moment, I will clear the doubts. Okay, is that fine?
Yes, sir.
Sure, thank you. So let's assume that point A and point B are at this center line. Okay, at this center line, and the distance between the point A and the upper surface of the mercury in the left arm is Z1. Say it is Z1. Okay, let me label it as Z1. In the case of point B, the distance between the point B and the upper surface of the mercury in the right arm is, say, Z2. Okay, these are two distances, and the difference between the height in the two arms, okay, is, say, delta H. Okay, delta H. Okay, so I hope the notations are clear. So
Yes, sir.
yes, so now what we'll do is that compare the two heights of mercury in the U-tube shaped manometer, and you will choose the lower level as our datum. Okay, datum means the point of reference from which we will measure our pressures. Okay, from which we will take our measurement, just something like that. So they will consider the point C, since it is at lower level, to be our datum. Okay, so now from the principle of hydrostatic law, that is basically dP by dz is equal to minus rho g. This hydrostatic law, I guess it was discussed very properly in the lectures. So we know that within the fluid, if the 2 points are the same height, the pressure must be the same, right?
Yes, sir.
Since point C and say this point D are at the same level, the pressure at point C must be equal to pressure at point D. Okay, so this is the first fundamental concept that we have to catch, that pressure at point C is equal to pressure at point D. Okay, so this is the first step we have written. This is clear, right?
Yes, sir.
We have chosen the lower level of the mercury in the U-tube manometer and chosen that as our datum. We will not do any measurements below it. All our measurements will be above this red line. Okay, that's why this is our datum. Let me just write it, datum. Okay, so since point C and point D are on the same level, so pressure at point C would be equal to pressure at point D. So PC is equal to PD. It's clear. Now what we'll do is we look into the factors that will add up or that will cause the occurrence of pressure at these 2 points. Okay, so what are those factors? First is the pressure, the inherent pressure at point A and point B. That's clear, right? Sonalika?
Yes, sir.
Yes. So there is some pressure difference. So there is some value of pressure at point A and point B. That's the first thing. Then this liquid column from A to C, it will have some it will exert some pressure on point C, right? This liquid column.
Yes, sir.
Yes. So similarly now, can you say in the case of the left arm, what are the factors that will cause us to have some pressure at point D? You tell me.
Sir, pressure at B, and sir, from B to sir D.
B to D. That's true.
Yes, sir.
But you can see that now there are two different fluids in the case of B to E and E to D. Am I correct?
Oh, yes, sir. Yes, sir.
Yes, sir. For there's pressure at point B, but from B to E there is water. So you need to consider that. And then E to D again there is mercury. So you need to consider both of them separately, primarily because the densities are different. Right?
Yes, sir.
Yes. So now we just have to balance it. Okay, that's now it's very simple. If you know what are the things that are causing the pressure to occur at these 2 points, now you just need to balance it. So for point C, we know that there is pressure at point A. So this is PA plus Z1 into rho WG. I hope you know this formula, that P is equal to, for hydrostatic condition, P is equal to rho G H.
Rho GH.
Yes. So we are just applying that formula here. So Z1 is this length, Z1 to rho W, this density of water, into G. Okay. So this is the pressure because of this liquid column. Okay. So
Yes, sir.
at point C, this is done. This is done. Similarly, let us do for the left arm at pressure at point D. PB, this is done, PB plus now Z2. Right, we have labeled it as Z2. So Z2 rho W into G, that is this one. It is clear, right? Z2 into rho WG.
Yes, sir.
Rho W because it is water in that case.
Water.
Yes, and finally this column, that would be rho Hg, density of mercury, into G, this acceleration due to gravity, and now this difference I told was delta H, right?
Yes, sir.
This is delta H, right? Z1 minus Z2, so this is the height, it is delta H. So rho Hg into G into delta H. So our balance is done. Now just rearrange the terms, take PB here, so PA minus PB because PA is greater in our case. Then rho W into G, these two terms, rho W into G into Z2 minus Z1, this term will go there, and finally we have rho Hg into delta H into G. Okay, so this statement is clear.
Yes, sir. So why the P pressure at A is greater than pressure at B?
Yes, I told you, right? You rightly mentioned that since the flow is occurring in this direction, you told that pressure at A must be greater than pressure at B. And I also told that for the flow to occur, we need a negative pressure gradient. A negative pressure gradient. This basically means is that as we move towards the positive x direction, the dependent variable, that is P in this case, would decrease. That would result in a negative pressure gradient, right? That will lead to this derivative to be negative, right? A decreasing function, something like that.
Yes, sir.
Yes. So you can just even consider it to be something as a consequence of two different magnitude of forces. Say there is pressures at this point, say this is PB, and the force that is exerted here is say PB into this certain area A1. Okay, and here the pressure exerted is PA into A1 say pressure is force is pressure into area, right? So
Yes,
since
sir.
since the force at the net pressure at A is greater than, since area is same, so if the pressure at A is greater than pressure at B, it basically means that the force at this region is greater than force at this region, right?
Yes, sir.
So if the force is greater, so the net movement of the liquid, this liquid would be towards this direction, right? This force is greater, so it will move the liquid in this direction, right?
Yes, sir.
Yes, so it basically means that this higher force is pushing the fluid through this pipe, and that's why pressure has to be lower in this case, because the areas are the same.
Yes, sir.
Okay, so it's very nice that you're asking these doubts, because eventually when we go ahead in the course, say we are reading flow through pipes or even the Navier-Stokes equation, you will eventually see that these are the concepts that come into picture. And now if you're able to, and then if you're able to recollect or compare these two phenomenons, correlate these concepts there, then it will be very helpful for you to understanding the course in the best way possible. So that's why I was mentioning such things. Okay.
Yes, sir.
Okay. So since up to this point the derivation is clear, now it's just the rearrangement of the terms. This PA minus PB is equal to rho WG Z2 minus Z1 plus rho HG delta H into G. Now again Z2 minus Z1 would be minus delta H, because Z2 is lesser than Z1. So Z2 minus Z1 would be equal to minus delta H, right?
Yes, sir.
Yes, then finally, just since delta H is common in both these terms, just take out G delta H would be into rho Hg minus rho W. So PA minus PB will be equal to G delta H, take rho W common, rho W into rho Hg minus rho W minus 1. Okay, so this is how you measure the pressure difference at two different points in a pipe using a manometer. Okay,
Yes, sir.
so is it clear or how to uh, use the principle of manometry to find the pressure difference between any 2 points in a pipeline or any, say, flow measuring device? Is it fine now?
Yes, sir.
Yes. So see, the concept is very simple. Just revisit the concept. I guess this exact definition, its exact derivation is done by Professor Chakraborty in the lectures. Just go through it once. Once you're able to catch the concept, I don't think there will be any problem regarding manometers that you will not be able to solve. Okay. Okay, so I think that's all for the theory part. Now just let us just go to the questions, so that that will be helpful for you to solve the assignment questions for this week. So let me just go. Okay, so just go to the questions. Okay. Okay, then it's very simple. The questions are on the screen. I'll give you some time to solve the question. Then there's solutions already there. Detailed solution I've already written. So we'll just then compare our solutions. Okay. So is it fine, Sonalika?
Yes, sir.
Okay then. So let's go through the questions now. The first question is very simple again. Uh, Small gas bubbles form in a soda when a bottle or a can is opened. The average bubble diameter is 0.2 millimeter. Estimate the pressure difference between the inside and the outside of such a bubble. It is given that the surface tension of the soda gas interface is 0.0728 Newton per meter. This is basically our sigma. Okay, so you are asked to find the excess pressure, the pressure difference between the inside and outside of such bubble. Okay, so can you do it? I guess it's very simple. Just use your calculator if you have. Uh, Put the values in the expression and tell me the answer. You can take some time, obviously, no issues. Is the question clear?
Yes, sir. Sir, it's asking about the pressure difference.
Yes. The formula that we saw, right? Delta P is equal to 2 sigma by R for a liquid droplet, and delta P is equal to 4 sigma by R for a spherical bubble or spherical bubble. So we need to now know which one to implement, whether the bubbles that arise from the a soda can they be considered should they be considered as bubbles or droplets. I guess
The
it's
bubble.
I guess it's written in the question itself.
Bubble.
Yes, just substitute the values here and tell me the answer. It's very simple.
Sir, 2.91 kilopascal.
Okay, so let me just check it. Yes, so the correct answer is D. Okay. Okay then. So similarly, let's just go to the second question. Okay. An atomizer forms water droplets with a diameter of 10 into 10 to the minus 5 meter. What is the pressure outside the droplets at 20 degrees Celsius if the pressure within the droplets is 102 kilopascal? Assume the surface tension of water at 20 degrees Celsius to be 0.0728 Newton per meter. Okay, I will give you some time to see the question. Try to analyze it and tell me what are you asked to find. Okay, and then go ahead and solve for this question. Okay, just view the question for some time and just tell me what is asked to find here in this case. What is being asked?
Sir,
Yes.
the outside pressure.
Okay, so since I guess you already know what to find, can you please solve it? I guess it's very simple now.
Yes, sir.
So in this case it is water droplet instead of a bubble, so you need to use the appropriate formula again. Use that and just tell me what should be the outside pressure.
Sir, answer B.
B.
Yes, sir.
Okay, so let us just, so can you tell me the steps so that I can just write it on the screen?
Yes, sir. So first, del P, the pressure difference, so 2 into surface tension coefficient by R.
Sure.
certain
So what does
certain
that turn out to be?
so 2.91 2.91 I think.
2.91.
Yes sir.
This is divided by
Kilopascal.
okay, kilopascal. Then what did you do next?
Sir, certain pressure difference means P outside minus P inside
Okay.
is equals to del P.
So you just did P out is equal to delta P plus P inside. Right?
Yes sir.
Okay.
Yes sir.
So the everything is correct, but just at the last moment you did the mistake. So this one is wrong. It should be the other way around. Can you tell me why now? Why it should be the other way around? I think we discussed it thoroughly.
Sorry sir, I'm not able to recall.
Sure, no issues. Okay. See, everything is correct. Just I told the conceptual part is bit wrong. So it would be P out would be P inside minus delta P. So P inside is 102 minus 2.91. So it should approximately come around this one, 99.09. Okay. See,
Yes sir.
see what happens is that, say, take a scenario. It is given that the pressure inside the bubble is 102 kilopascal. Okay. And you're telling that your pressure is turning out to be 104.87 kilopascal, right? So just assume a scenario that there is a spherical bubble here which is a very thin layer. Yeah, you know it's very thin, right? When you pop a liquid bubble, a soap bubble, it just pops out. It's very thin, right? So if you're saying that the pressure outside is greater than P inside, what would happen to this bubble? Won't it collapse? Because of the
Yes sir, Kola.
it would collapse, right? Because the outside pressure is greater than the inside pressure. But in reality or in our day-to-day life, we see that the bubble is able to maintain its shape, right? So it must
Yes
happen.
sir.
It must happen that the inside pressure should be greater than the outside pressure, right? Is it?
Yes sir.
Yes. And but one may again ask, what if why if the bubble is able to maintain its shape, why shouldn't it be equal? Like why the inside pressure should not be equal to the outside pressure? Because can you tell why there is a requirement a bit of excess pressure for the bubble to maintain its shape? Why so? And you can see it's very less compared to the atmospheric pressure, only 2.91 kilopascal compared to 102 kilopascal, say. Why is it? Why there's a need of a bit of extra pressure for the bubble to exist?
Sir, so I think there is gravitational मतलब सर जो weight की वजह से उसका
नहीं, it's not gravity. Obviously gravity is there, but say if the bubble is floating, think in the perspective of uh, surface tension. Are you able to analyze?
no sir.
Sure, no issues. Okay, just try to understand it this time. We discussed it in the just a few minutes before, but still, okay, it's fine, no issues. See, in the case of surface tension, as you told that the water surface or the liquid surface tries to stretch itself, right? Stretch itself. What it means? If it is stretching, there is a force that is being exerted on its surface, right? And by the inherent nature of surface tension, these stretching forces would try to make the net surface area of the liquid to be as small as possible. Okay, and if you know that for a given volume, for a particular volume, the smallest surface area possible is for a spherical shape. Okay, so what happens is that there is an pressure that is being exerted from within the sphere. Okay, let me just zoom it. Yeah. This, in this sphere there is a pressure that is being exerted within the sphere. Okay, from the inside of the sphere there is a pressure inside the sphere. Let us call it P in. Okay, P in. And again from outside, because of the atmospheric existence of atmosphere, there is an pressure from the outside of the spherical bubble. Are you able to understand this image?
Yes, sir.
Right, the outside atmosphere will exert some pressure on the surface of the spherical bubble to compress it, and within the bubble itself there is a pressure that is pushing the bubble up towards the outward direction. Okay, so that it is able to maintain its shape. Okay, but along with the outside pressure forces, this inside pressure force must also balance the surface tension forces. Why? Because, say, if you consider one half of the sphere, the surface tension forces, what they will do is, let me use this color, what they will do is they will try to compress the bubble even further. Like, even if it is of spherical shape, it will try to make this bubble even smaller. Okay, because there are some stretching forces that they will try to compress the bubble even smaller. Okay, these surface tension forces, they will try to do that, and that's why this inside pressure must be able to balance the outside pressure as well as the surface tension forces, which is trying to compress or collapse the bubble even further. So is it clear?
Yes, sir. So
Right.
the surface tension forces are compressive in nature, or
See, you compressive, I don't think that would be correct word, but it would be something like it tries to make the surface of the liquid as small as possible. Okay, so it does not want to expand, it does not want the liquid molecules to move apart, it wants the liquid molecules to stay together. So if this if this spherical bubble, say there is a certain number of liquid molecules within this spherical bubble. Okay, so these bubbles, if the size of this bubble increases, what would happen is that the liquid bubbles would move further apart, right? Liquid molecules would move further apart, right? Is it understandable?
sir, audible?
ठीक है, ठीक है. Okay, so uh, within this liquid surface there are, say, n number of liquid molecules. Okay, okay.
Yes, sir.
Yes. Now, if this bubble, the size of this bubble increases for some certain reason, what would happen is that these molecules will move apart, right?
Yes, sir.
Right. Since the number of molecules is constant and you are saying that the size of the bubble is now increasing, these liquid molecules will move apart, right?
Yes, sir.
Yes, but it is not what surface tension wants. The surface tension wants that these molecules should stick together and should not move apart. These molecules should be as close as possible. Okay, so
Yes, sir.
this, what will happen is that because of this tendency of the surface tension forces, it will try to make this bubble as small as possible. If not at all compress it, like completely, it will try to completely deflate it, like I want to make it as small as possible. I don't care, I don't want the bubble to be big, I want it to be very small as possible, so that these liquid molecules are as close as possible. Now are you able to capture it?
Yes, sir.
Yes, and that's why, because of this tendency of the surface tension forces to make this bubble as small as possible, this inside pressure inside the bubble will have to overcome the outer atmospheric pressure as well as the surface tension forces to maintain the integrity of this bubble or droplet. Okay,
Yes, sir.
Is it clear? Just say, is it clear, or you still have any doubt?
Sir, my question is, sir, there is the name is surface tension.
Yes.
Sir, then sir, I have that doubt कि sir जो फोर्स का नेचर मतलब सर सरफेस टेंशन तो एक फोर्स ही है सर, उसका नेचर क्या है, मतलब वो कंप्रेसिव है या फिर टेंसाइल फोर्स है?
वही तो मैं दैट इज व्हाट आई वही तो मैं कहने की कोशिश कर रहा हूँ. ये कंप्रेसिव भी नहीं है, टेंशन भी नहीं है, बट ये इस तरह का फोर्स है जो चाहेगा कि जो लिक्विड मॉलिक्यूल्स है वो इतना पॉसिबल हो अपने पास रहे. अगर ज़रूरत पड़े तो कंप्रेसिव फोर्स की तरह बिहेव कर सकता है, या टेंसाइल की तरह भी बिहेव कर सकता है. कंप्रेसिव और टेंसाइल आपको तभी दिखने में आता है जब आप एक से कोई बार का आप स्टडी कर रहे हैं, राइट. अगर if you're studying a bar, say if you're studying a bar, and if the forces are trying to pull it, you can say these tensile forces. If the forces are in this direction, you say this is compressive, right? But in the case of
Yes,
surface
sir.
tension, there is no such characteristic that I can say that it is completely compressive or tensile. Say, अब क्या होगा? Okay, take this example. This is a surface of water. यहाँ में these are liquid molecules here. Okay, so what happens is that जैसे कि like our Professor Chakraborty was giving some example that we pour a liquid, drop a bubble on this surface. Okay, an immiscible bubble on this surface. Okay, so what would happen now? This surface will deform something like that. Okay.
Yes, sir.
Yes. So what would happen is that now to maintain the integrity of the surface, that now the liquid does not want the surface to break, because if it breaks, if the interface breaks, the liquid molecules move apart, right? So it does not want that. Like as long as possible, I want that the liquid molecules should stick together. So what would happen is that these molecules would pull each other, something like that. Okay. Okay. So now you can observe that even though and in this case you can observe that there is a kind of force that is trying to pull these liquid molecules towards each other. So for this liquid molecule, say for this particular liquid molecule, this molecule experiences a kind of a tensile force. Okay, is it understandable that since this molecule is
Yes,
being
sir.
pulled by both the sides, this liquid molecule experiences a tensile force, right? A kind of tensile force that is pulling this, that is being pulled by all other molecules. Not only this molecule also pull this molecule, and this molecule will also be pulled by this molecule. So there is a kind of interaction, a tensile force between these molecules. Okay, is it
Yes,
understandable
sir.
now? But now you may ask, if this tensile force, why this bubble is being compressed? Okay, that's the catch. Say this is a membrane. This is a membrane here. Instead of assuming it as a surface, assume that these are balls. These liquid molecules are balls, and this red line is a say it's a carpet or a cloth. Okay, something like that, above which these balls are being placed. So in order to pull these balls together, in order to pull these balls together close to each other, this what would happen to this cloth or this particular fabric? It will fold, something like that, right? It will try to fold itself, right? समझ पा रहे हो?
Yes, sir.
हाँ,
Yes, sir.
ये कपड़ा फोल्ड हो जाएगा, it will fold. Even though the molecules are experiencing a tensile forces that is pulling them closer to each other, the fabric itself that is holding these molecules is being compressed. Not actually not compressed, but shrinking. It is being shrunk, right? In order for these molecules to get closer to each other.
Yes, sir.
Now you understood, right? So,
Yes, sir.
but this shrinking is just an physical example, okay, but not what is actually happening. Just now apply the similar concept to the surface of the bubble. So for the liquid molecules to come closer to each other, the fabric that is holding the outer fabric or the surface of the liquid bubble should shrink, right? So that these molecules are coming closer to each other. Okay, is it clear?
Yes, sir.
हाँ, then पर ये completely shrink नहीं हो सकता. It cannot collapse completely because there is an pressure inside the bubble itself, which is actually balancing this shrinking tendency of the bubble as well as the pressure applied by the outer atmosphere. Now you're understanding, right? There are two forces that the inside pressure is able to balance. What are they?
Sir, the surface tension forces and sir, atmospheric pressure.
Yes. So both of them, the atmospheric pressure and the surface tension effect, has a tendency to shrink the bubble, to compress the bubble. But the pressure inside the bubble has a tendency to push the bubble outside, push the surface of the bubble outside, because ये इस तरह से act कर रहा है, it is acting in the outward direction. And in equilibrium conditions, this pressure forces as along with the surface tension forces are balancing each other, and that's why the integrity or the shape of the bubble is contained. वो वैसा ही रहता है. And that's why
Yes.
and that's why the inside pressure should be higher than the atmospheric pressure for the liquid bubble to coexist. Now you got it, right?
Yes, sir.
हाँ, like बस conceptual में भी अगर आप if you are clear, you will know that this pressure, that is outside pressure, cannot be larger than the inside pressure. हो ही नहीं सकता. It is not possible. And that's why you can rule, if you are getting some answer that shows that the inside pressure is greater than the outside pressure is greater than the inside pressure, you can just rule out that option. Okay?
Yes, sir.
I hope the concept is clear now.
Yes, sir.
Okay. So see, as Professor Chakraborty also mentioned in the class, the surface tension is a very complicated topic actually. It's not something that could be taught in one or two classes at an undergraduate level. Not something like that. It's a very immersive and very, how to say, complicated topic to understand or even visualize. But there can be different methods to at least give an essence of surface tension, if not at all the complete physics. Okay, so this is just a small essence of surface tension rather than the entire physics. Okay, so
Yes, sir.
for time being, for at this level or the level of the course that is trying to the level that the course is trying to achieve, at this point of time, this much of concept is enough. But if you're really interested, obviously you can go and read about this topic even further, but for the sake of this course, I think this much knowledge is enough. Is it clear?
Yes, sir.
Yes, but obviously we highly appreciate your doubts, that you're interested in such topics, so we insist that you go on asking such doubts. But if you want to know further about surface tension, I will highly suggest that you read some books that are exclusively related to surface tension. Okay?
Yes, sir.
Okay then, thank you. So just now let's go to the other remaining questions. So I think this question is a simple derivation, but it's a good exercise again. So, and it was done by Professor Chakraborty in the class. So if you have notes, you can just tell me the answer directly, but let us just go to the question. Okay. Determine the contact angle of the liquid droplet shown in the figure. Here sigma is the surface tension, actually surface tension coefficient, and the subscripts S, L and V denotes solid, liquid and vapor respectively. Okay, so this is the, say, droplet on the surface, and SLV denotes the solid, liquid and vapor interfaces. Okay, and this is the contact angle theta. So we have to find an expression for angle theta. Okay, so it's just a basic force balance. If you have attended the lectures, I guess Professor Chakraborty has derived this expression himself in the class. So if you have the answer or derivation, you can directly tell me the answer. But if you want to do it right now again, I will give you some time to do it. Then you can tell me the answer. Is it okay?
Yes, sir.
It's just a force balance.
So, theta is equals to cos inverse sigma SD minus sigma SL by sigma LP.
Yes, absolutely correct. So this is,
Option D.
yes, it is derived in the lectures. So I don't think we should go uh, go go ahead and derive it again. But still, for the sake of other students, we'll just go through just show the diagram and the derivation. I hope this is what you have done, right?
Yes, sir.
Yes, it's just a force balance along the horizontal direction. So sigma SL is the force towards this direction because of the interaction between the liquid and the solid. Again, the sigma SB is the force along this direction, negative x-axis direction, because of the interaction between the solid and the vapor interface. And this component of the sigma LV is towards this direction, so it would be sigma LV cos theta. Now you may ask that sigma is actually the force per unit length, why are you not considering length? So if you consider the length to be constant with basically the perimeter of this bubble for all the expression, you can just cancel out the length, right, as discussed by Professor Chakraborty. So we just do the force balance, that is sigma SL plus sigma LV cos theta is equal to sigma SB. You can cancel out the L from all the terms. Then theta would be cos inverse, just take this term in this side, so sigma SB minus sigma SL divided by sigma LV is equal to cos theta. Then to find a theta, you just take the inverse, cos inverse of this term, so it will be theta will be equal to cos inverse sigma SB minus sigma SL by sigma LV. Okay, it's very simple. You can go ahead and check the lectures, but it's fine. Okay, so let's go to the next question then. Okay, I need to zoom out a bit. Okay, so option is none of this, so I think you can skip that. Okay, which among the following figure correctly represents the shape of meniscus of mercury in a glass capillary? Again, a very conceptual type question. We just discussed it. Can you tell the answer?
Yes, sir. So option A.
Option A. So absolutely correct. So can you tell me the reason behind it? Why is it so? Why it is showing?
Sir,
Yes.
yes, sir. Sir, in mercury, sir, the adhesive force is lesser than the cohesive force, and the angle obtained with the meniscus is obtuse angle.
Yes, absolutely correct. So that's the reason. They're actually correlated, like because of the fact that the adhesive forces between the mercury molecules and the glass is lesser than the cohesive forces between the mercury molecules. That's why the meniscus formed by the mercury in a glass capillary is a obtuse angle. Okay, but yes, but if at all a scenario arises that say there is a element or there is an element in which the cohesive forces between the mercury and that particular element is stronger than the adhesive forces between the mercury molecules and that particular element is greater than the cohesive forces between the mercury molecules, in that case the meniscus would be of a different shape. Okay, and that's why it is told that the capillary rise also depends on the material of the capillary tube as well. Okay, so
yes, sir.
yes, so I hope it's clear. Now let's go to the next question. Okay, I hope this question is again very conceptual. It's a one line answer. If you know the answer, you can just tell me. Determine the excess pressure in a cylindrical liquid jet over a pressure of surrounding atmosphere Here sigma is the surface tension and r is the radius of the jet. So I guess this is again very simple. Can you tell that? I just discussed in the lectures today, in the session itself.
Sigma by r.
Yes. I'm sorry. It's sigma by, okay. And again, if you just want to know derivation, it's again very simple. See, the expression that we get, P is equal to 2 sigma by r, or delta P is equal to 4 sigma by r, is just the simplification of this generalized expression. Okay, this generalized expression. I will not go on to say what is r1 and r2. It's basically the curvature of the particular shape that we are considering. Say this is the fabric, or fabric of the surface of the bubble or a liquid jet that we are considering. So this surface has two curvatures. Let me just draw it. It has two curvatures, right? First is this one. This is certain curvature, and this has a certain curvature. So this curvature has, say, radius r1, and this has r2. So in the case of a liquid jet, what happens is that, and it also mentioned it is spherical liquid jet. So one of the surfaces becomes straight or horizontal or vertical, whatever you may consider. So this is what a liquid jet looks like. Okay, I hope this is,
Yes, sir.
it is clear. So in this case, what happens is that one of the curvature is, say, r1. Say r1, that is r1 is equal to r, or small r in this case. But the second curvature, this curvature r2 becomes infinity, because it's essentially a straight line, right? And 1 by r2 would give this term to be equal to 0. And if we take one, whatever way, if we take r1 is equal to r, then delta p would become sigma by r. Okay, from this expression. I hope it is understood, right?
Yes, sir.
Okay, thank you. So now we go on to see the next questions. So question 6 and 7, it is common data type question. So the question is, a vertical clean glass piezometer tube has an inside diameter of 0.5 millimeter. When a pressure is applied, water at 20 degrees Celsius rises into the tube to a glass height of 25 centimeter. Okay, water rises to a glass height of 25 centimeter, and the inside diameter is 0.5 millimeter. And when a pressure is applied. Okay, so these are key terms. I am underlining it. It is given that the vertical surface tension of water is, it is given that the surface tension of water is 0.0728 Newton per meter. Contact angle is 0 degree, and the density of water is 1000 kg per meter cube. And this is the value of G. So determine the capillary rise in the tube. Okay, it is again a very simple question. Just substitute the value in this expression. And just tell me the answer, like what would be the answer in this case? Capillary rise. You understood the question, right?
Yes, sir.
Yes, just tell us like what will be the capillary rise. Did you get the answer? Capillary rise.
No sir, sir आंसर सर मेरा सर 0.19 आ रहा है, लेकिन सर ऑप्शन में तो
0.19 आ रहा है, तो लेट्स जस्ट टेल मी द वैल्यू. चलो वैल्यू बताइए मुझे. चलिए मैं ट्राई करता हूँ. एच होगा आपका 2, राइट 2. सिग्मा क्या है
0.072
cos 0 फिर आपका 1 होगा.
1. यस सर.
रो 1000 है. G 9.81 एंड R क्या है आपका 0.25 नहीं है ना. R हाँ 25
डिवाइडेड बाय 2. यस सर.
हाँ इंटू -3.
3.
हाँ तो इसका आपका 0.19 आ रहा है. Let me
तो
check.
वाला 0.059 हो रहा है.
हाँ 0.059.
यस सर.
हाँ then it is almost equal to 6, right? So ये होगा 0.06.
Yes sir, sir, but there is a height of 25 centimeters.
हाँ वो हम क्वेश्चन को दोबारा पढ़ेंगे, राइट. सो ठीक है. कैपिलरी राइज आपका है 0.059 मीटर, राइट. इट इज इक्वल टू 0.06 मीटर. ठीक है, तो फर्स्ट का आंसर इज करेक्ट. तो सेकेंड में क्वेश्चन पूछ रहा है एस्टिमेट द अप्लाइड प्रेशर. तो क्वेश्चन वापस पढ़ते हैं. सो इट इज टोल्ड दैट a vertical clean glass piezometer tube has an inside diameter of 0.5 millimeter. Okay, when a pressure is applied, देखिए बता रहे हैं कि प्रेशर अप्लाई किया गया है. when a pressure is applied, water at 20 degree Celsius rises into the tube to a height of 25 centimeter. मतलब मान लीजिए कि हम एक मैनोमीटर यूज़ कर रहे हैं, बहुत थिन मैनोमीटर यूज़ कर रहे हैं, एंड वी आर ट्राइंग टू मेजर अ फ्लो थ्रू ए पाइप. मतलब प्रेशर डिफरेंस, वी वांट टू मेजर द प्रेशर डिफरेंस और स्टैटिक प्रेशर बिकॉज ऑफ द फ्लो थ्रू दैट पर्टिकुलर पाइप. ओके, एंड बिकॉज ऑफ दैट फ्लो देयर इज अ राइज इन द लेवल ऑफ द वाटर. ओके, along with the capillary rise. Capillary rise तो pressure हो ना हो, static condition में भी it will show some rise because of the capillary action, right? जो कि that is equal to this one. Okay, is it clear?
नहीं सर, सर आगे पढ़ो.
हाँ, what I mean to say is that, say it is told that in a container, में in a container, this is the capillary tube that or let me keep it like this. So in a container, this is a capillary tube or a very thin pipe. Let me just not a very thin pipe. Okay, now what happens is that there is a liquid here. Is the diagram clear?
Yes sir.
Okay, so because of capillary reaction a certain height of liquid ऑटोमेटिकली बढ़ जाएगा. ये फ्लूइड में आप प्रेशर डालो मत डालो डजेंट मैटर, बट कैपिलरी रिएक्शन के कारण बिकॉज ऑफ एडिसिव फोर्सेस बिटवीन द ग्लास सरफेस एंड द लिक्विड मॉलिक्यूल्स, द लिक्विड विल राइज अप नो मैटर व्हाट इज द इनहेरेंट कंडीशन ऑफ द फ्लूइड विद इन द कंटेनर, इट विल राइज अप, राइट. इस पर आप सहमत हो?
Yes sir.
हाँ, ये आप मानते हो, राइट. ओके, जो कि वी फाउंड आउट दैट दिस इक्वल टू 0.06 मीटर. ओके,
Yes sir.
yes, but then they are saying that they are applying some certain pressure to this liquid because of which the liquid has risen to a level of 25 centimeter. Okay, okay.
Yes sir.
हाँ, but this rise is actually the rise because of the application of pressure, applied pressure plus the capillary action. Is it clear? I will say it again. दोबारा कहता हूँ. सी, पहले इन्होंने एक्सपेरिमेंट के दौरान इन्होंने ये ट्यूब पानी में डाला और उनको शायद पता नहीं होगा, अनइंटेंशनली ही सही, द वाटर हैज रिजन अप बिकॉज ऑफ द कैपिलरी रिएक्शन. ओके, से डेल्टा एच,
Yes sir.
डेल्टा एच हाइट वो बढ़ गया और उन्होंने ध्यान नहीं दिया. द एक्सपेरिमेंटलिस्ट डिडंट लुक इनटू, उन्होंने कंसिडर नहीं किया, या फिर उन्होंने ट्यूब डालते ही प्रेशर अप्लाई किया पानी, जिसके कारण पानी राइज हो गया एंड वाटर हैज रिजन टू ए लेवल ऑफ से हाइट h. Total height is h. Okay, total height is h. Total height of liquid column is h in the glass tube water capillary. Okay, is this clear?
Yes, sir.
And this h they are saying it is equal to 25 centimeter. Okay, but
Yes, sir.
this total height is actually because of a small rise because of the capillary action, that is delta h, plus the applied pressure that they have put in the liquid. Is it clear?
Yes, sir. सर कैपिलर राइज की वजह से जितना हाइट और अप्लाइड प्रेशर की वजह से जितना हाइट.
देखिए, जब इन्होंने इनिशियली ये ट्यूब पानी में डाला, उसके कारण ये थोड़ा सा हाइट जो है डेल्टा एच, ये थोड़ा सा पानी ऊपर उठ गया. ठीक है, इट हैज़ रिजन अ सर्टेन लेवल, इट हैज़ रिजन अप टू सर्टेन हाइट बिकॉज ऑफ कैपिलरी एक्शन. ओके.
Yes, sir.
And then after they have applied the force, it has, say, I will use a different notation, then it will be helpful for you. And because of the applied pressure, पानी में applied pressure apply किया, से यहाँ में कुछ forcing किया या पानी को नीचे धकेला, जिसके कारण the liquid has risen up to a level of say capital H. Okay, capital H height और बढ़ गया. ठीक है. And now they are saying that when a pressure is applied, the water has rises into a tube to a height of 25 centimeter. तो ये total height जो है ये is equal to 25 centimeter. Okay.
Yes, sir.
हाँ, तो टोटल हाइट है 25 सेंटीमीटर, जिसमें से ये डेल्टा एच हाइट जो था दैट इज बिकॉज ऑफ द कैपिलरी एक्शन. डेल्टा एच इज ऑफ कैपिलरी एक्शन एंड ये हाइट जो रहेगा इट वुड बी एच माइनस डेल्टा एच. यू गॉट इट राइट?
Yes, sir.
हाँ, वही दैट इज व्हाट दे आर आस्किंग अस टू फाइंड राइट नाउ, बिकॉज वी नो दैट P इज इक्वल टू रो जी एच. और इस केस में बिकॉज ऑफ अप्लाइड प्रेशर वो H क्या होगा, रो जी कैपिटल H माइनस डेल्टा एच.
Delta H.
हाँ, तो जस्ट सब्स्टिट्यूट द वैल्यू, उसमें 1000 इंटू 9.81 इंटू 25 माइनस 6 इंटू 10⁻², या फिर और सिंपल in more simpler term, since let's keep it in meter, so 25 centimeter would be 0.25 meter minus 0.06 meter. Just do this calculation and tell me the answer then.
Sir, 1860.9.
Okay, so it is approximately equal to B.
Yes, sir.
So you got the understanding, right? You got the answer, right?
Yes, sir.
Got the concept, right? See, like ये थोड़ा मतलब अंडरस्टैंडिंग का बात है. Like see, when you are conducting an experiment, okay, say you're conducting an experiment, say in a lab, you're asked by your supervisor or your professor to he asks that you apply certain pressure P on the surface of liquid and see the height up to which the liquid has risen. Okay, and you say to your professor or your supervisor or lab expert that the liquid has risen to a height of h meter. Okay, is it clear?
Yes, sir.
But you forgot that this rise in the height is not only because of applied pressure, but also because of a certain amount of length of this liquid column has risen, also because of the capillary action as well, right? The capillary action would exist no matter what the diameter of your pipe is, right? It would obviously exist because there is an adhesive forces between the liquid and the glass molecules, right? So there would be a certain level of capillary rise in the glass column. But as the diameter of your this measuring device increases, of your glass tube increases, the contribution in this height because of the capillary action is very small. Do you get it? Why? Because
Yes, sir.
if this is h, and if your r increases, this h will go down, right? Agar r was initially say 1 millimeter and you increase the r to say 1 meter, this h will go down, right? Because if all the other parameters are constant, if the denominator increases, the this term should go down, right?
Yes, sir.
That only. So if the diameter or the radius of your measuring device, say the pipe or a tube, increases, the capillary rise would go down. It will become small. Okay. And that's why for most of the experiments you do not consider the capillary action in the case of manometers, because already the manometer that we use for measuring these pressure differences are large enough to ignore the capillary rise. But there is a capillary rise, whether or not you consider it or not, but there is a capillary rise. But just for the sake of simplicity of the experiments, we ignore the increase in the height of liquid column because of the capillary rise. Is it clear?
Yes, sir.
Okay. So this thing will come gradually, but it's fine. Okay. Just for your conceptual understanding. Okay then. So we are in the final question. So again, it's based on manometer. So I insist that either you take because the questions are below here. So I insist that either you take the screenshot of the question or of this diagram, or you can draw it. Okay, while I am dictating the question. Okay. So this is the final question. So the question is, a manometer is formed from a glass tubing with uniform inside diameter of 6.35 millimeter. Okay. The U tube is partially filled with water, and then V equal to 3.25 millimeter cube of oil is added in the left side. So they have, in this U tube manometer, they have added 3.25 centimeter cube of liquid oil in this manometer. Okay, this is the volume. V oil is equal to 3.25 centimeter cube. Assume that both legs of the U tube are open to atmosphere. Basically the pressure here and here is atmospheric pressure. Then we will look into questions. Okay, so is the question clear? The description of the problem clear?
Yes, sir.
So this is a manometer which has water initially, and they have added a layer of a column of oil here whose volume is
Oil.
3.25
3.2.
3.25 centimeter cube. Okay, so these are your given data, and the diameter of your manometer here is 6.35 millimeter. Okay.
Yes, sir.
Okay. Did you draw the diagram? Because now I have to scroll down, so this will get this will go up. This will not be visible on the screen once I scroll down. So can you draw the diagram and label it?
Yes, sir.
Just draw it. After you have drawn it, just tell me. Okay. Then I can scroll down and discuss the questions.
Yes, sir.
Okay, thank you. So, and you have written the values, right? Diameter value and the volume of the oil. You've taken this data, right?
Yes, sir.
Okay. So now let's just go to the questions. So the first question is, which among the following relationships is or are correct? I hope you have labeled the diagram accordingly. So they're asking that which among the following relations are true? That PA is equal to PC, PB equal to PD, PA equal to PD, and PB equal to PC. So which among the following statements are true? Just try to recall the principle of manometry that we have discussed thoroughly while we were discussing the theory part. Just try to
The
implement it. Yeah.
PB is equals to PT.
Okay, that's true. Is there any other statement that can also be correct? It is true, yeah. This one is correct. Is there any other relation that can also be correct? Let's go back to the question. I hope it will help you. So in the question they have told that a manometer is formed from glass tubing with uniform inside diameter of say this, as shown in the figure below. The U tube is partially filled with water. Then V is equal to 3.25 centimeter cube of oil is added in the left side of the manometer. Assume that both the legs of U tube are open to atmosphere. Basically, these two are open to atmosphere. So whether the pressure at point A and point C will also be equal?
Yes, sir.
Yes. See, in our previous case, rather than being exposed to atmosphere, it was actually submerged in water, right? We are measuring the pressure difference in a uh, pipe containing water, and these columns were filled with water. And since they were in the influence of water, we told that these 2 points are having different pressures because these are at different heights. And also in this question, if they wouldn't have mentioned that these two are explicitly open to the atmosphere rather than being in a pipe that is measuring, say, the pressure difference in a gas, rather than saying it, they've explicitly said that these two ends are open to atmosphere. So basically trying to say is that PA is equal to PC is equal to PATM. This is the definition of this statement. Okay. Both legs are open to atmosphere. So it basically saying is that PA is equal to PC is equal to PATM. And that's why this statement is also correct. Okay. It's also correct. Okay. So let us discuss the next question. Which among the following expressions is or are correct? Okay. Now you have to just apply the manometric principle that we have discussed. Maybe try to balance the pressures from a certain datum and just tell me the answer.
Yes, sir.
Sure, please. Any progress?
Still options are not matching.
Okay, can you tell me your answers? Like, what did you get?
Yes, sir. So PA plus rho oil GL is equals to PC plus rho
Wait, slow, slow,
WG
slow. PA plus rho oil. Okay, rho oil G
oil GL.
H
L, sir, L.
L is equal to
PC
yes,
plus rho W
yes.
G L whole L minus H.
Okay. So you basically get PA minus PC would be rho W GL. Sorry, it's rho L GL. Okay. So let us go to a diagram. Okay, I guess we can take this as well with us. Copy, paste. Okay. So if you recall, I think I have. Okay, so you have uh, basically to taken this as your datum and then done your measurements, right? Okay.
Yes, sir.
Okay, so let us try to see whether we are able to get your options back from this expression. So okay, instead of your initial statement would have been PB is equal to PD, right?
Yes, sir.
Okay, so I guess now it is now it is simple. So instead of measuring the pressure difference between point A and point C, let's try to take each terms individually. Okay, each side individually. So this basically means that PB would be equal to PA plus rho oil GL. Is it correct?
Sir.
So if you're from this statement to this statement, if you go, it basically means that PB is equal to PA plus rho oil GL, right?
Yes, sir.
Right.
Yes, sir.
So we can write PB minus PA is equal to rho oil into GL.
Yes, sir.
Okay. So let's do a similar thing to the left hand side as well, right hand side as well. That PD would be equal to PC plus rho water G L minus H. So we can write, is it correct? Is it what we are trying to state, right?
Yes, sir.
So we take PD minus PC is equal to rho W G L minus H. So are these two in the options?
Yes, sir.
Okay. So if you go back, I guess B and C are the options, correct options, right? B and D, sorry.
B and D.
Yes. Okay. So see, your concept was absolutely correct, right? There's no mistake in what you are trying to obtain, but since this difference term is not there in this one of the options, so in order to achieve, to cross check whether these options are correct or not, try to obtain one of these pressure differences, because these two are not correct, these two are absolutely not correct. So try to obtain expressions that are within the option, and if after finding the pressure difference, if these expressions do not match with your right hand side, then you can say this, that none of the options are correct. But since the difference that you're trying to obtain is not one of the options, among one of the options, then it is difficult to correlate your answers, right? So you have to use different tricks so that you are able to obtain the options, right? Obtain the correct
Yes,
options.
sir.
Yes. So see, in this case your concept was correct, but since the question didn't contain your option, even though you're conceptually correct, but we cannot give you marks, right? Because it is not one of the options. You need to tick one of the options, right? So for such kind of questions, you need to think a bit like how to get the options, like is the answer possible? Okay, is it good?
Yes, sir.
Okay, then let's just go to the final question. Calculate the equilibrium height h. It is given that the specific gravity of oil is 0.827. Okay, so you can just take your data, take the specific gravity of oil. It basically means raw oil by raw water is 0.827, which is understandable.
0.8.
Which is understandable, right? Density of oil is always lesser than water. That's why it floats over the water. At least
Yes, sir.
this oil. So yeah. So you have to find the value of h. And I will tell it's very simple. Actually, it's just the trick is to find L. Before finding h, you need to find L. And how you find L? Have you taken the data? Let us go to the image itself so that we can solve it. You have taken this data, right?
Yes, sir.
Oh.
D and V.
D and B?
Sir, D diameter and V, sir, volume.
Okay, sure. So let us go to the diagram here. Okay. So we are asked to find this h, height, this height h. Okay. So to do that, let me give you a hint. You need to find the value of L. Okay, and can you find the value of L?
Yes, sir. So can try.
Okay. Try and tell me the value of L first. Are you able to find L?
Sir, PP minus P is different. तो उसका वैल्यू
मतलब अप्रोच सही था, but like you were overlooking a very fundamental concept. Obviously there are approximations, but let us see. Okay, so we need to find the value of L. So L is given here. Okay, L is given here. Moreover, more importantly, the volume of the oil at this region is given, right? Is that correct?
Yes, sir.
So if you assume that this liquid column is in the form of cylinder. That's a very good approximation. Like if you just ignore the liquid heights in the meniscus, this region, if you just assume it to be flat and assume it to be a cylinder, you can consider this liquid column to be of a cylindrical shape. Okay, it's a very good approximation, right?
Yes, sir.
Is it clear?
Yes, sir.
Yes. So what is the volume of a cylinder? What is the formula for volume of a cylinder?
Sir, pi r cube h. Pi r square h.
Yes, right, pi r square h. So, and since r is not given, so let us write pi d square by 4 into h, right? And h, instead of h, let us just write l, because h is equal to l in this case, correct?
Yes, sir.
Yes. Now, since we all know all the terms except l, we can directly find l from this expression, right? Just do the calculation. It would be, say, 3.25 into 10 to the power minus 6, right? If you can convert centimeter cube to meter cube.
Yes, sir.
Yes. And it would be 3.1416 into diameter is 6.35 into 10 to the power minus 3 square. Just do this calculation and tell me the answer.
Sir, 6.516 into 10 to the power minus 4.
This calculation has given you 6.516 10 to the power minus
4, sir.
4. I am getting 0.1026 meter. Can you just revisit your calculation? It is 4 into 3.25 into 10 to the power minus 6 divided by 3.1416, that is pi, into 6.35 into 10 to the power minus 3 whole square.
Yes, sir. Sir, that mistake.
Okay, sure. Do that. So let me just write it. So if you do that, I guess you will find 0.102 meter approximately.
Yes, sir. 0.
Okay. So now, in order to find h, so I guess we can take the help of this expression, right? Because it is the only expression where we have explicitly h written, right? Correct?
Yes, sir.
Yes. So now it is told in the question that PA is equal to PC is equal to PATM, right?
Yes, sir.
So we can cancel out both of these terms from the equation.
Yes, sir.
Then it will basically give us rho oil G into L is equal to rho W G into L minus H. Now you understand why I asked you to find L.
Yes,
Because
sir.
since you know L now, the only unknown here is H. So we just need to rearrange the terms now. So we can write it as rho oil, you cancel out G from both the sides. Rho oil by rho W L is equal to L minus H. Rearrange it even further. H would be equal to L minus 1 minus Sg. So it is basically 0.102. 1 minus, what was the specific gravity of oil?
0.827.
Okay. Can you do a calculation now? Just tell me the answer. What will be the value of this calculation?
Yes.
Sure.
Sir, 0.017.
Meter, right?
Yes, sir.
So let us just see whether it is one of the options. So this would be this one, right?
Yes, sir.
Okay. So I guess that's all. So that's all for today's session. So I hope it was helpful for you.
Yes, sir.
Okay. Okay then. I hope. Thank you for attending the class. Like it was also very interesting for me to have such an interactive session. So I hope that you join next week's session as well. Okay.
Yes, sir.
Yes. Not only mine, but there are also other TAs. You can attend those sessions as well. But I will just insist that you do the assignments properly and watch the next week lectures very nicely, okay, so that we can discuss and have a very interactive session in the next week. Okay.
Yes, sir. Thank you, sir.
Sure. You have any doubt from today's session?
सर
Yeah.
ये सर 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 जो सिलेंडर क्यों कंसिडर किया मतलब वो
ये वाला
यस सर
क्योंकि ये कह रहे हैं दे आर सेइंग दैट इट्स अ यूट्यूब मैनोमीटर, राइट? यूट्यूब मैनोमीटर है. सो बेसिकली होता क्या है, these are actually glass tubes that is shaped in the bent in the shape of a U. Okay, so ये actually ऐसा होता है. It is hollow tubes actually. तो कोई भी लिक्विड अगर इन इस कॉलम के अंदर रहेगा then it will be cylindrical, right?
यस सर
तो ये cylindrical shape ही तो लेगा. I was saying that it may happen that because of the presence of the meniscus, वो जो curved upper surface होता है वाटर के केस में, देयर कैन बी सर्टन अप्रोक्सीमेशन इन्वॉल्व कि वो हम लोग जो कर्व सरफेस का वॉल्यूम जो है वो हम लोग डिसरिगार्ड कर रहे हैं. पर अगर उसको हम लोग डिसरिगार्ड भी करें देन कंसिडरिंग दिस कॉलम एज ए सिलेंडर ए सिलेंड्रिकल वॉल्यूम इज ए वेरी गुड अप्रोक्सीमेशन, राइट?
यस सर
इसलिए हम लोग ने सिलेंडर लिया था.
यस सर
Okay then, so कोई भी डाउट हो, if you have any doubt please you are most welcome to ask the doubt in the next session as well, or discussion forum में you can ask your doubts. Okay, we will try to address them. Okay.
यस सर
Okay then, thank you so much. Meet you in the next session. Okay. Sure. Okay then, I will end the class. Thank you. Sure.
यस सर
Sure. Thank you.